Hi all, I think we should get started. I'm Nancy Briggs. I'm the manager and one of the statistical consultants with Stat Central. For those of us who've never had any contact with us, I'll just give you a brief intro to what we do. We are a team of statisticians and consultants, and we are tasked with helping researchers across UNSW with their statistical analysis and research design. If you're an HDR student or a faculty researcher in any area of the university, you can come to us for some general advice and help with your statistics and data analysis. We run monthly seminars that are open to everyone on basic statistical issues, which is what we're doing here today. And today we have Mark Donoghoe, who is one of our consultants. He does some work with the Kids Cancer Center in the hospital here on campus. And he's going to talk to us today about p-values, which is something that we all use all the time when we're analyzing our data, and sometimes we use them incorrectly. So he's going to tell us what they are and how we can correctly use and interpret them. Let's welcome Mark and enjoy his talk. Thank you.
All right, thanks, Nancy. Hopefully everyone can hear me all right. This is going to be recorded and put on the Stat Central website along with the slides if you want to be able to download them later. So if I can just ask, normally in person I'll take questions during this, but I can't see the at the moment, so if you can just hold your questions to the end, I'll be happy to take them all then. All right, so let's get started. So here, this is a video. I couldn't work out how to get this to play sound from my computer through the Blackboard app. It will be embedded in the slides again if you download them. But what I'm going to do is paste the link to this video in the chat, and you can click it and watch it. It just goes for 90 seconds. I've just put it in the chat now. So if you want to go and watch it, it's very short. There might be an ad first, I'm sorry, but yeah, click on it and just scroll down a little bit and watch. I'll give a couple of minutes to do that, and then I'll start talking again. All right, so hopefully most of you were able to watch that, and it's finished by now. Sorry for talking over the end if it hasn't. For those of you who didn't watch it, the question was basically, what is a p-value? And the video is of a bunch of people struggling to answer the question. They might be laughing or stumbling over their words. And these weren't just regular people. These are scientists. This video is taken at something called the Metrics Conference, which is apparently a conference about meta science, or the study of studies. So apparently all of them could actually give the correct technical definition of a p-value, but they couldn't put it in clear, simple English. So from that same article where you found that video, I thought this was a kind of nice quote. You can get it right, or you can make it intuitive, but it's all but impossible to do both. So given that constraint, maybe I've off a bit more than I can chew by giving a talk about p-values, but I'm going to give it a go. So you might have heard about the reproducibility crisis. So reproducibility is the idea that if you didn't do an experiment and someone else repeats it, you get largely similar results. So there is this famous and somewhat controversial paper which said that most published research is actually false and couldn't be reproduced. And this apparently resonated with a lot of scientists. This was a survey done by Nature of over 1,500 researchers, and 90% of them said that there was either a significant crisis or a slight crisis. So the dark red and the light red areas of that graph there. And this got picked up in kind of your more general media. So this was an article in Slate asking, is science broken as a result of the reproducibility crisis? So what's the reason for this? Well, the reason seems to have been pinned on the dependence on p-values and statistical significance. So we saw articles like these. So the problem with p-values, the one I linked to before from 538, saying not even scientists can easily explain p-values. And a particular journal even went as far as banning p-values. So if you can't see the highlighted sentence at the bottom of that, it says, from now on, Basic and Applied Social Psychology journal is banning the null hypothesis significance testing procedure from their journal. All of this led to the American Statistical Association taking an unprecedented step of releasing a public policy statement about a particular statistical method. This is something they've never done before. And this statement is 4 years old now. Oh, sorry, I'm hearing a lot of dings in my ears. So,
somebody just commented the audio is a little bit choppy. It sort of goes in and out a little bit, and everybody's saying yes. But I don't think that there's anything. I don't think there's much that we can do.
Yeah, I can't change where my microphone is, unfortunately. Try turning my video off. That's a good idea, actually. We'll see if that helps things. Apologies for that. Going back to the ASA statement. So this statement was published in 2016, so it's 4 years old now. But I think it's got some good messages, and this is what's going to form the basis of the talk today. So I'm going to start with the definition of a p-value. So this quote comes straight from the ASA statement. They say, informally, a p-value is the probability under a specified statistical model that a statistical summary of the data, for example, the sample mean difference between two compared groups, would be equal to or more extreme than its observed value. So this is the idea that you choose a summary statistic that captures the effect that you're interested in. Maybe it is the difference between two groups that you're comparing. You work out what the distribution of that summary statistic would look like under a particular model. And from that, you calculate the probability that it would be more extreme, as extreme or more extreme than the summary statistic that you actually observed. So this is kind of my alternative, which is even more informal. It is saying that the p-value is the probability that a particular random number generator would generate a number bigger than the one you observed. So you've observed the number, and you're going to compare it to the probability that a particular random number generator gets a number bigger than yours. So in this sense, the specified statistical model that's mentioned in the ASA definition can be thought of as a random number generator. So if you're doing a t-test, it's generating numbers from a t-distribution, which is like a normal distribution. If you're doing a chi-squared test, like the name suggests, it's generating numbers from a chi-squared distribution. And so the p-value is just looking at that distribution of randomly generated numbers and seeing how many of them are bigger than the one that you observed. This definition is a little bit cynical, I guess, but it's kind of designed to demonstrate how abstract the idea of p-value is, I guess. So the ASA statement contains 6 principles for the proper use and interpretation of p-values, and I'm just going to go through each one of them briefly and kind of talk a bit more and explain each one. So principle 1 says that p-values can indicate how incompatible the data are with a specified statistical model. So firstly, I want to emphasize incompatible. So they're measuring incompatibility, not compatibility. But secondly, I want to emphasize specified statistical model. So the statement's a bit abstract because it's trying to be very general, but most of the time, this model describes how we think the data would be generated under a null hypothesis. So if you're doing a t-test under the null hypothesis, we're saying that we're drawing from our 2 samples from t-distributions with the same mean, for example. Or from normal distributions with the same mean. So a small p-value suggests that it's unlikely that the specified model would produce data as extreme as what we actually observed. So that can kind of point to one of 2 things. It might be that the model is right and something unlikely just happened. So things that are unlikely happen all the time. It's possible that something unlikely happened in your case. So if the model is right and you conclude that the model is wrong, you've made what we call a type 1 error. The other possibility, if you find a small p-value, of course, is that the model is wrong. But how is the model wrong? There's a famous quote in stats that says all models are wrong, but some are useful. But there are lots of ways that our model could be wrong. The assumptions, the distribution of the outcome. But when we see a small p-value, we usually assume that it means that the H0 part of the model is wrong, and we take this as being evidence against the null hypothesis. And that might also be right, the right decision. Principle 2 says that p-values do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone. So these, you might have seen these explanations for p-values in the literature before. They're just wrong. And I'm going to do a quick poll just to kind of demonstrate this idea, I guess. So this might take me a tiny bit of time to set up because unfortunately I wasn't able to put it in advance. Just bear with me. All right, so hopefully a poll has popped up for everyone. Have a vote. So we're saying that our null hypothesis is true, H0 is true, we're going to say that our model is accurate as well. So our specified statistical model is true. Which of these is more likely? So one is that we're going to get a small p-value, so something that might be significant or kind of borderline significant, if you want to call it that. Second one, p is kind of reasonably large. It's between 0.5 and 0.6. The third one is that those two options are equally likely. And the fourth one is that we need more information. So maybe people can see the answers now. I didn't click anything, but it looks it's made them visible. So the correct answer is actually number 3. They're equally likely. So you're just as likely to get a small p-value less than 0.1 as you are one that's between 0.5 and 0.6. And without any more information, I guess we can say that much. So when the null hypothesis is true and the model is accurate, p-values are uniformly distributed between 0 and 1. So you can think of it just as a random number, randomly picked between 0 and 1. So you're just as likely to get a small p-value as you are to get a large one. So that should kind of give you a hint as to the fact that they don't say anything about the probability of the hypothesis being true, because when it is true, it's just a random number between 0 and 1. But if you want to kind of get more detailed, a p-value is calculated from a model assuming that our null hypothesis is true. So because we've assumed it's true to calculate the number, we can't use it to say anything about the probability that our assumption is true. You can't assume something and then talk about the probability that your assumption is true. Kind of getting even more technical from a frequentist point of view, it's said that kind of models and parameters are fixed. They're fixed values we're trying to work out, whereas data are random, so you're randomly sampling data. And p-values describe the probability of random data, probability that you would see the data that you got given the model. It doesn't make sense to talk about the probability of a model because this is not a random variable. So in other words, a p-value is a statement about the data in relation to a particular hypothetical explanation, which is the model. It's not a statement about the explanation itself. So it's not a statement about the truth of the hypothesis. It's a statement about the data. So principle 3. So we've talked about, I guess, the interpretation of a p-value and what it means, and this is getting into the territory of how we should use them. So principle 3 is saying that scientific conclusions and business or policy decisions should not be based on whether a p-value passes a specific threshold. So I think the number one thing when thinking about this is that a p-value is a continuous measure, and a conclusion doesn't suddenly become true on one side of a divide and false on the other side of a divide. So the classic one is using a significance level of 0.05. You'll often read in papers like, we showed that ABC, and then in brackets P equals 0.02, as if that's proof that you've shown it. Or on the other hand, you might read something like, there was no difference between X and Y, and then in brackets P equals something big, so 0.3. So in the first example, saying is that we've got a small p-value. That means that the data is surprising if the null hypothesis was true. In an indirect way, you can say this is evidence against the null hypothesis being true. but it doesn't necessarily mean that it's false. So it's not proof that the null hypothesis is false. It's just evidence that kind of points in that direction. In the second example, goes back to principle one. So principle one, we said that a p-value measures incompatibility with a specific model, not compatibility. So a large p-value doesn't imply that the model is true. You might have heard the kind of famous little phrase that absence of evidence, not evidence of absence. In kind of simple terms, in real life, if you don't look very hard for something and you don't find it, you probably wouldn't conclude that it doesn't exist. So if you do a small study and don't find a difference, that's not kind of evidence that there is no difference. It's just that you didn't look for a difference, I guess. So some people say that the only conclusion from a large p-value is that you need to get more data. So what about the situation where you're pondering a p-value of 0.049, which is just significant, and comparing that to one which is just non-significant, so 0.051. So I think the thing just to remember in that situation is how many assumptions and approximation built into calculating this p-value. So this goes back to the idea of thinking about our null hypothesis model being like a random number generator. For your p-value to be accurate, you need this random number generator to be pumping out random numbers exactly like what they would look like if the null hypothesis was true. So if you're using a t-test or a z-test or something, nothing in the world is truly normally distributed. The distribution, they can get close to normal distributions as you get bigger and bigger samples. The exact distribution of test statistics are often based on asymptotics, which is what happens when your sample size gets infinitely large. And you never have an infinitely large sample size. So your null distribution is never exactly the distribution that you're using to do your test. Those asymptotic results can be pretty accurate when your sample size is kind of reasonable, even if your assumptions are a little wrong, but they're not perfect. So that's why I kind of say not to get hung up on these little tiny differences in p-values. They're both kind of telling you the same thing if they're slightly different from one another. So this is a nice article. Again, if you download the slides, you'll be taken to this link, or you can just Google this phrase. This is the title of the article, which is kind of catchy and captures this point, saying that the difference between significant and not significant is not itself statistically significant. But the kind of retort to this principle is that, well, that's all well and good to think of p-values as continuous measures, but I do need to make a decision. In pragmatic situations, you often require a yes or no decision. Do we continue to do tests on this hypothesis? Do I give my drug to these patients? Does this drug get approved for funding? Absolutely, you have to make these decisions. But principle 3 is just saying that you shouldn't use the p-value on its own to make that decision incorrect. You also need to take into account other things like the study design, measurement quality, the validity of the assumptions that went into the calculation, and external evidence. So just saying whether the p-value is one side or the other of a magic line is not going to give you the 100% best answer to the decision that you're interested in. So principle 4 is saying that inference requires full reporting and transparency. So what does that mean? So strictly speaking, if you're going to get really technical, for a p-value to have its desired interpretation, the calculation of it has to account for all of the data-dependent decisions that you made along the way. So for example, you might check for normality before deciding whether to do a t-test or a rank sum test. You might test for equal or unequal variances to see which type of t-test you'll do. If you're doing a chi-squared test, you you might first check if you've got an expected number in each cell of at least 5. And if these checks decide which type of analysis you do, technically speaking, you should adjust your p-value for it. In reality, these examples are benign and they would have very, very little impact on the result. But when you do an analysis of data, you make a lot of decisions along the way. Some people call this the garden of forking paths. You have to make decision A, decision B, and it can lead you in completely different directions depending on what small decisions you make along the way. Who to include or exclude, how to define an outcome variable, and so on. So a good example of that is this many analysts one dataset paper. Again, that's linked there if you download the slides. So this was an example where 29 research groups looked at the same question with the same data set of whether football referees were more likely to give red cards to dark-skinned players compared to lighter-skinned players. So they all separately did their analysis, and 20 of them found a significant relationship between skin color and the likelihood of getting a red card, and 9 of them did not. So along the way, all of the 29 groups had to make lots and lots of decisions of exactly how to do this analysis. So even though they had the same data set and the same research question, they ended up in very different ending positions. So there's lots and lots of decisions that you have to make along the way, but it's nearly impossible to kind of correctly account for all of these decisions. So it's just another important reminder that a p-value is not an exact answer to the question you're interested in. It should give you an indication of what's going on, but like the actual number itself is not the answer to your question. So there are practices that will have more dramatic effects though. So these are things that you should definitely do because they completely distort the properties of your p-values and could lead you to the wrong conclusion. So don't look at your data and only perform a test if it looks like you're going to find something there. Don't do tons and tons of tests and only report the ones that reach significance. That's what led to that paper saying that over half of research findings are false. And don't change your analysis until you get the result that you want. So don't try lots of different ways of doing it until you get something nice. That some people call that p-hacking, and that's definitely no. What should you do though? Well, be transparent. Report all of the analyses and the decisions that you make along the way. And then someone who reads it can kind of, in their mind, weigh up how strong they think your evidence is. So just as an example of that, type 1 error gets inflated if you do lots of hypothesis tests. Most of you might have heard of this multiple comparisons problem. If you randomly generate lots of random numbers, some of them are going to be small just by chance, right? There is a decision whether or not to adjust for that. Just for multiple comparisons. Sometimes it's really obvious that you should, sometimes it's not so obvious. But either way, it's important to report all of these tests so that the reader themselves can weigh the strength of evidence against the likelihood of a type 1 error. Rule 5 says that a p-value or statistical significance does not measure the size of an effect or the importance of a result. So it's a fact of being a scientist that we need to use words that have a very specific meaning, right? So unfortunately, sometimes these words are also used in everyday speech with a less precise meaning. So example, in chemistry, the word organic is very specific. In physics, the word work means something very specific. I can't remember exactly what it means, but statistics seems to have been become especially good at using common words to mean something very specific. We use regression, likelihood. A good one is consistent, which means something very specific in stats. And this usually doesn't cause problems because in context, they usually can't be confused with the non-technical definition. But there is one word that seems to be particularly troublesome, and you can probably guess what it is. significant. So a p-value conflates the magnitude of an estimate with its precision. You can get a small p-value by taking a precise measurement of a tiny effect. So you can get a significant result when there's an unimportant effect, or a non-significant effect, if you want to confuse the two words. Or you can get a large p-value by taking an imprecise measurement of a large effect. So statistically significant doesn't mean conventionally significant. It doesn't mean the effect is important. And kind of on that note, principle 6 says, by itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. So you might be familiar with confidence intervals. So these describe the range of parameter values that are consistent with the data. Some people prefer the term compatibility interval because it kind of better conveys this idea of being a range of values that are compatible with the data. So typically, a small p-value corresponds to a confidence interval that doesn't include the null hypothesis. But you can get, but both of these confidence intervals have exactly the same p-value. So they both exclude 0. At the first one, it looks like the difference is very small, and the data isn't compatible with effects larger than 0.01. And in the second example, the second confidence interval, it looks like the effect is very large, and the data isn't compatible with effects smaller than 3.3. So just looking at the p-value alone wouldn't give us this information at all. And the same thing can happen in the other direction. If you've got a non-significant p-value, your confidence interval is going to include the null. But again, that might be because you've really precisely measured a really small effect, or you've imprecisely measured an effect which might be quite large. You don't know if it's large in either direction. And again, just looking at the p-value doesn't tell you that. So the important takeaway is that when you report a p-value, you should also report the effect size and a confidence interval so that people can make that comparison. And to help them make that comparison, you should do it on a meaningful scale. So in these examples, in interpreting them, I've kind of assumed they're on the same scale, but this small and this large. But for people to be able to judge whether an effect is small or large, the scale that you use in reporting the effect size has to be meaningful to them. All right, so those are the 6 principles. I think they're pretty good principles. This statement was kind of met with some controversy by statisticians. Some of that was just because of technical reasons that are probably not important or interesting to the majority of people. But others thought that the statement kind of didn't go far enough. This group here, I'm not sure if this is too small to read, suggested that the default significance level should change from 0.05 to 0.005. Another group suggested that maybe we should redefine p-values so that they answer the question that we're actually interested in and not this indirect question about incompatibility. Said that the concept of statistical significance should be retired altogether, and over 800 statisticians co-signed this statement, and that in itself kind of caused controversy. And all of this led to a follow-up editorial by the ASA people who wrote the first one. The point of this was to kind of address the criticism that the first statement contained a lot of don'ts, what not to do, but not much guidance on what you should do. So this was part of a special issue of the American Statistician, which was called Statistical Inference in the 21st Century, a World Beyond P less than 0.05. It's permanently open access. It's got 40 articles in it with suggestions on what you should do about this issue. So I recommend checking it out if you've got the time. But what did they say? They kind of condensed their do's into 4 things, which kind of were summarized with the mnemonic ATOM. So accept uncertainty. So just know that a p-value is not going to give you a definite answer. Be thoughtful, be open, be transparent, and be modest. I would say it's kind of also important to focus on So that example we saw before, where you can get the same p-value with very different estimates. There's no need to discard p-values altogether, but consider their limitations. And I think it's especially important to remember that a p-value is on a continuum. Just comparing it to a fixed level is not the right way to go about it. So they were originally designed to be considered as continuous. There was no strict rule about comparing them to a fixed level, and it was only when they kind of got mixed together with this approach to inference that brought about this idea of null hypothesis significance testing. And they weren't kind of originally designed to do this. But it is true that the interpretation of p-values is difficult to understand and explain intuitively. And so that the possibility of misinterpretation leads some people to say that they should be discarded altogether. And those people often argue that Bayesian inference uses a more natural and intuitive interpretation of probabilities. And that's definitely something to consider as well. So this is just some further light reading. The first two are just the original ASA statement and the follow-up in the special edition. This is a nice guide to misinterpretations about test p-value, confidence intervals, and power. And then this one's one I just found the other day, which is a nice article written by a kind of science communicator, with some tips for talking about statistical significance. So thanks a lot for your time, and I'm happy to take questions.
So you can either raise your hand or type the question in the chat, and Mark can answer them.
Okay, I can see one question here. Could you please explain again the statement that P is on a continuum? Okay, yeah, that's just the idea that comparing P to a fixed level and just to do good science, because firstly, it's not like a completely accurate number. There's all these assumptions and approximations built into the calculation. But also that kind of anytime you reduce a continuous number into a dichotomous position, a dichotomous kind of decision, you're losing information. And that's kind of something Peter talked about at our last seminar. So yeah, it's just the idea that p-values are numbers between 0 and 1. They're not yes or no answers. So I can see a hand up.
Yeah, Christine had a hand up.
Yeah, hello.
Yeah.
Thank you so much, Mark.
No
so
worries.
I'm a physics education researcher. So I do education research, but in physics. Now, I've had an issue sometimes when I try to publish work where we're not necessarily including any statistical testing because we're reporting on preliminary data with small sample sizes. So we don't want to go too far in terms of claiming anything. We're just reporting on what we're seeing. So 6 students did this, 20 students did that. But sometimes we get reviewer feedback saying you must report on statistical significance and do statistical testing. How would you recommend responding to such requests?
Yeah, that's a very tricky one, because this idea that statistical significance kind of gives you the truth is kind of well entrenched. So you were saying it's a situation where you think it's inappropriate to do a statistical test, or?
Yeah, because often we're not claiming that this is clearly better than something else, or significantly more students do this or the other. We're not necessarily interested in such claims. We just want to report on we collected this data, this is what we saw, it's interesting, and we would, suggest looking further into this, whether it will affect how we should best teach physics.
Yeah, so I would say in that situation, I think confidence intervals and focusing on the estimation part of it is the important thing. So maybe what the reviewers are kind of getting at is saying that, you've done a survey or a experiment or something, but there's some uncertainty in your results, and you need to kind of quantify that uncertainty. You report that 20% of students like this way of teaching or whatever. There's some uncertainty about that 20% number. It's almost certain that that's not the exact number if you were able to survey the whole population. So I would suggest putting confidence intervals or some measure of uncertainty around any kind of estimate that you report, just so you give an idea of kind of the sampling error that's involved in that.
Okay, thanks. And do you have a good article that we can bring up in the response to editor or reviewers to just support that statement?
Or off the top of my head, I can't think, but I know there are good ones out there. I would suggest have a look through that that special edition, which is where that second ASA statement is. There's 40 articles that follow that up, and I'd say it's pretty likely at least one of them makes that argument, because this is one of these arguments that comes up along with the p-value thing, is that people should focus more on estimation and not significance.
Thank you so much.
No problem.
Hey, Mark, there's a question in the chat window about Bayesian statistics from Mary.
Oh, yeah, okay. So you're an engineering researcher about Bayesian stats. Would a Bayesian idea resolve these misunderstandings of p-values? Yeah, good question, Mary. Yeah, so a lot of people argue that the Bayesian interpretation of statistics and probability is kind of more intuitive. So in frequentist statistics, probabilities are kind of quantifying these hypothetical infinite number of experiments and how many you'd expect to see, how often you'd expect to see something happen. Whereas in Bayesian statistics, it's the parameters that are random. So the probability of it raining tomorrow is a random value, let's say. And in that sense, it is appropriate, it's okay to talk about the probability that the effect is this big, or the probability that the effect is this small, or whatever. In p-values, they're talking about the probability of the data. In Bayesian statistics, you're talking about the probability of the parameters or the effects in your model. And a lot of people argue that that's kind of more appropriate. And a lot of people argue that using Bayesian statistics is kind of easier to interpret. Yeah, and that kind of leads to Tay's question. So if frequentist is so problematic, why don't we use more Bayesian? Good question. One of the practical reasons is that frequentist statistics is computationally easier. So to do Bayesian statistics, you have to combine what's called your prior probability with the likelihood in the data, and that's simple in only very simple cases, and you need a lot of computational power to do that kind of in a general case. Computational power is becoming more and more available, so more and more people are kind of turning towards Bayesian ideas. One of the kind of criticisms that people talk about with Bayesian statistics is that you do have to provide a prior. So you have to talk about your kind of maybe subjective probability of an effect so large before you do the analysis. And the results can differ depending on what you say that prior is. But other people say that's a strength in the sense that you have to make a strong specified statement about your beliefs about an effect before you do the analysis. So yeah, I guess the reason why people don't do it so much is because Frequentis got caught hold first because it's easier computationally, but it's becoming definitely more and more common. Okay, so there's a few more questions. Gila says, what's the best way to express the effect size in manuscripts? So I think just something meaningful. So if you say that an effect is not zero, which is what a kind of p-value, a small p-value might suggest, you also should give it a sense of what that effect is and make that something meaningful that people in your field will understand. So if you're talking about the effect of a drug on the risk of heart disease, you might talk about the change in risk for people taking the drug versus people not taking the drug, because that's something meaningful. If you're talking about changes in weight, a weight loss program, then giving the effect size in kilograms is something that makes sense to people reading it. So that definitely depends on the field, but just something to understand whether it's a meaningful effect size or not, I think is the most important thing. Question from Aaron. Multiple testing seems to be very important. Oh, okay. So question about multiple comparison adjustments. So kind of, yeah, so the multiple comparison adjustments, a lot of them are kind of based on the assumption that the tests are independent of one another, which isn't often the case. If you're testing like outcome variables that are related to one another, for example. But there are kind of specific methods that do perform better, like when you think your outcomes are positively correlated and negatively correlated. There are specific tests for if you're doing pairwise comparisons between multiple groups. There are specific adjustment procedures that are designed for that situation. So I would just say, yeah, have a look into them. There are some that perform better when you've got correlated outcomes, and depending on whether positively correlated or negatively correlated, and they don't just only work when they're independent. David says, I would argue that Bayesian approaches are not well equipped to test specific null hypotheses. Is there an effective treatment? Is Y related to X? Yeah, that's a good point. Some people, I think, argue that the null hypothesis is never true. That's not a debate I'm going to get into. So Bayesian people would say that you want to test things about whether the effect size is smaller than an amount that's not important, rather than whether it's exactly zero or not. But yeah, that's a good point, David. Thanks.
Are there any other questions? Okay, thank you all for joining us. If you are interested, The Division of Research is holding their Hacky Hour health session right now. So if you want to, I think they have a Microsoft Teams event going on right now, and you can get answers to your data analysis and data storage questions. So thank you very much for joining us, and we hope you join us next month as well.